This is Chemical Processes for Micro and Nanofabrication. I'm Chris Mack, and this is Lecture 43, Part 1 of a two-part series on projection imaging for lithography. Our reading is section 7.6 of our textbook by Campbell. Let's review a little bit about what we've learned about diffraction so far. Remember, when light passes through a mask pattern with all the edges and features of opaque and transparent regions on the mask, light propagates away from the mask towards the lens, and we call that propagation diffraction. In lithography, we can describe diffraction in the Fraunhofer regime. That is, we're interested in the diffraction pattern a long ways away from the mask. The distance from the mask to the lens is, tens of centimeters away, on the order of a meter. And that is far enough away to be in the Fraunhofer diffraction regime, which is the far field. And in that regime, we found that mathematically the diffraction pattern is simply the Fourier transform of the mass transmittance function. The mass transmittance function is the transmittance of the electric field through the mask. We often approximate that transmittance function for simple mass as a binary function, a 1 in the clear regions and a 0 in the dark regions. We found that small patterns diffract more. The frequency components of the diffraction pattern vary inversely with the dimensions on the mask. So if I squeeze down the features on the mask, I spread out the features of the diffraction pattern. And finally, if I have repeating patterns on the mask, such as spaces and lines that are arranged in an array, but it could be other features, holes, contact holes in an array, or any pattern that repeats itself over and over again, the resulting diffraction pattern becomes discrete diffracted orders. The diffraction orders, in fact, the diffraction pattern in general, is a transform of the mass pattern. As such, it contains all of the information that is contained in the mass transmittance function. So all of the information about the pattern, the pitch, the size, the spacing, the shapes of the patterns on the mask, all that information is represented in the diffraction pattern. For the case of a pattern of lines and spaces, the pitch is contained, the information about the pitch of the mask pattern is contained in the positions of the diffracted orders, and the amplitude of the orders encodes information about the duty cycle, that is the width of the space divided by the pitch. We're going to use this idea of diffraction orders as containing information as we continue on our discussion of imaging today. Now, the Fourier transform is our way of calculating what that diffraction pattern is. So let's quickly look at some Fourier transform properties. I'll list them here without going into much detail. And in fact, in the homework for this part of the class, you're going to be asked to derive some of these relationships. First, linearity. Fourier transform is a linear function. So if I add two mass transmittance functions, I can, for example, f and g being added together, multiplied by scalar constants, I can take the Fourier transform of that sum as the sum of the Fourier transforms. This allows us to use superposition to simplify and make some of our problems easier. If I know the diffraction pattern for a single space, I can use this superposition to determine the diffraction pattern for a pair of spaces, for example. The shift theorem. If I have a mass pattern and I know what its Fourier transform is, then I take that mass pattern and shift it to the side. So shift in x by an amount a and shift in y by an amount b. I get the diffraction pattern that I would get without the shifting, multiplied by this term, which is a phase tilt. So this says the phase is varying linearly with fx and fy. So the same shape to the diffraction pattern, but a tilt in the phase is a function of position in the diffraction plane. Similarity, that is, if I grow or shrink a known pattern on the mask, scale by factors of a and b in x and y, for example, then I can get back the diffraction pattern, also scaled by a and b, but 1 over a and 1 over b. And this gives us the idea that if I scale this to be smaller, I end up scaling the diffraction pattern to be bigger. If I scale the mass to be bigger, I end up scaling the diffraction pattern to be smaller. And finally, convolution. The convolution theorem says a convolution in the mass plane turns into multiplication in the frequency plane. All right, those are just some properties of Fourier transforms, some of which might prove useful later. Also, it's useful to show a table of Fourier transforms. This is really one of the advantages of the Fourier transform approach to optics. Fourier transforms are very well known. Lots of people have already done Fourier calculations. And in fact, most of the interesting and useful mass patterns you might come across, you can imagine that somebody's already calculated the Fourier transform. And in fact, many people have tabulated these Fourier transforms. One of the good things about this approach is often you don't have to do the calculation yourself. You can just look up the answer in a table. So for example, here is that isolated space. So we have a rectangle function which describes this space. It's 0, 1, 0. It's a unit width, and we get the sinc function, unit width sinc function, as our answer. A step function which corresponds to an isolated edge on the photomask. We can see what the resulting diffraction pattern looks like. A delta function, which is a point of light, turns into 1. Yeah, see, this is called a Fourier transform pair because you can go back and forth between them. But a delta function has a Fourier transform of just 1. Makes it very easy. But what is 1 from the perspective of light? A delta function is a point. What does 1 mean? 1 means it's unit amplitude light that's the same everywhere. Well, that's called a plane wave. I have the same amplitude of light everywhere on the xy plane. That would be a normally incident plane wave. And on and on. This table, in fact, comes from my textbook, Fundamental Principles of Optical Lithography. And I now have my first excuse to pitch my book. I wrote this book published about 6 years ago, and it is a graduate level textbook on the topic of optical lithography. So if you're interested in getting into more detail than we're getting to here and just in this course, then I highly recommend this textbook. I will be referring to the chapters on lithography by Campbell as I go through these series of lectures on lithography. But there's a lot of material I'll be covering that isn't covered in Campbell. And so you can either look at this textbook, Fundamental Principles of Optical Lithography, or you'll just be forced to follow along with the lectures and use these lecture notes as your materials. So that's our review of diffraction and a little bit about the Fourier transform. What happens next? Well, as we said, if we have a mask with various features on it, and I shine light on the mask, the result is diffracted light that spreads out away from the mask. If, for example, I have a pattern of lines and spaces on the mask, we know that the diffraction pattern will be diffracted orders. That is, rays of light coming out at specific angles and traveling in one direction. So a question is, what happens next? Well, what happens next is the light goes through a lens. The lens is called the objective lens, sometimes called the imaging lens or the focusing lens. And this lens captures some portion of that diffraction pattern. But what portion? Well, the lens is not infinitely big. It can't capture everything. These diffraction orders keep on going until it covers all of space. But our lens is only, has a finite diameter. We need to describe how big this lens is and know how much of the diffraction pattern gets captured. We could just express the diameter of the lens, right? Well, that turns out to be not the most useful way of measuring the size of the lens. Instead, rather than specifying the diameter of the lens, I would like to specify the maximum half angle of light that can make it through this lens. We call that alpha. Half angle because it's measured with respect to the optical axis, this axis running right through the middle of the system. The lens is symmetrical about it. And if any of the diffracted light has an angle larger than alpha, that light will not make it through the lens. It won't make it through the aperture, the opening at the front of the lens. So alpha is the maximum half angle. Given that definition, we will define the size of this lens by a term called the numerical aperture. And the numerical aperture will simply be the sine of this maximum half angle multiplied by the refractive index of the media that the light is traveling through. In this case, the media is just air, and the refractive index is about 1. We're going to find out, though, that we can change that refractive index, and we'll talk about that later in a topic called emergent lithography. But for right now, we'll assume that we're operating in air, and the numerical aperture is simply the sine of the maximum half angle of light that can make it through the lens. This numerical aperture will prove very useful in understanding how the lens operates on the diffraction pattern. Before I talk about that, though, I'll make an appeal to anyone in the audience who might be an amateur photographer. Now, I know we're all amateur photographers because we all have cell phones with cameras on them, or we have point-and-shoot cameras. But there are a few of us left in the world who have a camera that's not automatic everything. And there's a little dial on the lens. These would be these big cameras that has a dial, and you can open and close the aperture. All right, that would be this opening here, which looks like it's fixed, but in fact, this opening can be put on an iris that opens and closes. And I can change the aperture. I can change the numerical aperture of the lens. And that's quite useful in photography to be able to change the numerical aperture of the lens. But in cameras, we don't call this aperture size the numerical aperture. Instead, we call it the f number or the f-stop. And there's little numbers printed on the outside of the lens as you flip through, 11.2, and I can't remember all of them, 8.6 or something. These are f numbers. F number is simply, this would be now the distance to the film, the distance from the lens to the film, B, divided by the diameter of the opening, A. And the f number is simply 1 over 2 times the numerical aperture. So while in amateur photography we have something called the f-stop, it's in fact the exact same concept as the numerical aperture, just expressed in a different way. All right, one last topic that relates to the definition of numerical aperture. Most of the imaging tools we use in lithography are magnification tools. In fact, they're reduction tools, so they have a magnification less than 1. 4x reduction means a magnification of 0.25, and the object, which is the mass pattern, is reduced by a factor of 4 before it becomes an image at the wafer. Well, not only are the dimensions of the features reduced, but the angles are increased in proportion. So, in fact, it's the sine of the angles. So if I look at a particular ray of light coming out of the mask, and the sine of the angle well, let me look on the mass side. The sine of the angle on the mass side, sine theta m, would be here. If I multiply that by the index of refraction in the media, which is generally air, this quantity, n times the sine of the theta m, will be multiplied by the reduction ratio, r, to get the same quantity on the wafer side. So if r is 4, let's say, then the index of refraction on the wafer side times the sine of the angle on the wafer side will be 4 times bigger than the quantities on the mass side. So the angles get bigger. And you see that in this picture. One of the things we see then is the numerical aperture is also 4 times bigger on the wafer side compared to the mass side. If I had a 5x reduction system, then the ratio would be 5. If I had a 10x reduction system, the ratio would be 10. The numerical aperture on the wafer side is r times bigger than the numerical aperture on the mass side. Now, it all works out. If I think about patterns on the wafer side, I should use the wafer side numerical aperture. If I think about patterns and their dimensions on the mass side, I should think about the numerical aperture on the mass side. I will get the same answer either way I look at it, because everything is adjusted by this factor of this reduction ratio, r, and all the numbers work out exactly the same either way. We also notice that the entrance and exits of these lenses are given names. The pupil is another name for an opening. And somewhere in the middle of this lens is something called the aperture stop, which actually constricts or limits the range of angles that can pass through the lens. If I look at the image of the aperture stop, that is, if I look into the lens on the entrance side, I will see this aperture stop, and what I see is called the entrance pupil. This is the image of the aperture stop when looking through the front of the lens, and the exit pupil is the image of the aperture stop when looking through the exit side of the lens. And we can think of the entrance pupil as where the light goes into the lens. We can think of the exit pupil as where the light comes out of the lens. All right. With that little caveat and description, let's now talk about the diffraction pattern as it goes through the lens. Here's a graph of the diffraction pattern that we've seen before for the case of equal lines and spaces. These are all diffracted orders. We've got the 0 order in the middle, the +1 order, the -1 order. Here's the +3 order and the -3 order. The even orders all have amplitudes of 0 for the case of equal lines and spaces. Now, let's draw on the same graph a picture of our lens. Our lens is an opening. The lens opening has a radius, and the radius is the numerical aperture divided by the wavelength. Remember that spatial frequency, which is the axis we're plotting on, is the sine of the diffracted angle divided by wavelength. So it's the maximum sine of the diffracted angle that can make it through the lens. That's nothing more than the NA. So I can draw a picture that says all of the spatial frequencies bigger than NA over lambda or smaller than minus NA over lambda are blocked by the lens. And all of the spatial frequencies that are within this radius of NA over lambda pass through the lens. I can see very readily which diffracted orders make it through the lens and which ones don't. Here's a top-down view. Of course, I was just looking at a cross-section before. Really, our lens is a two-dimensional shape. And in this case, the 0 and plus and minus first order go through. To make things even a little bit more clear, here's a 3D kind of perspective. If I have a mask pattern with lines and spaces that are all oriented vertically on the mask, when I shine light on it, where does the diffraction occur? Well, the diffracted light spreads out left and right if my line patterns are oriented vertically. So the 0 order will land in the middle of the lens and the plus and minus first orders to either side. if I rotate the mask so that my lines and spaces on the mask are oriented horizontally, then my diffraction patterns will spread vertically. So I'll get 0 and plus and minus first orders spreading vertically for that orientation of the line space patterns. Now I've exaggerated the size of these lines and spaces that I've drawn on these masks. Really, you know they're very, very minute in dimensions, not as big as this, but I just drew them big so that you'd see them and understand their orientation. So you can imagine now how, knowing the numerical aperture and the orientation of the lines and spaces, I can figure out where the diffracted orders land and which diffracted orders make it through the lens and which ones don't. Now we ask, what does the lens do? Well, let's think about this for a moment. Diffraction produces a diffraction pattern equal to the Fourier transform of the mask. Now, what do I want the lens to do? I want the lens to form an image of the mask. And I want that image to look like the mask. Well, if I think of it from a simply geometric perspective, light comes in, it's bent by the lens, and it focuses down to a point. All the diffracted orders will turn into plane waves that are focused down to the image. We can define the image plane as the plane where all the diffraction orders arrive together in phase, so we get constructive interference between these diffracted orders. But probably a better way to think about it is Fourier optics. If we want an image to look like the object, and the light going into the lens is a Fourier transform of the object, what we would really like our lens to do is take an inverse Fourier transform. And in fact, that's what a lens does. A well-designed, ideal lens, in fact a perfect lens, would be a lens that produces an image that's equal to the Fourier transform of the light that enters the lens. All right, now we've got diffraction, which produces a Fourier transform. The diffraction pattern is the Fourier transform. We've got a lens, which produces another Fourier transform. This time it's the Fourier transform of the Fourier transform. What does that do? It gives us the original back. Now we've got an image that looks like the object, just like we would want to have, with one little exception. The objective lens does not take the Fourier transform of the entire diffraction pattern. It only takes the Fourier transform of the portion of the diffraction pattern that can make it into the lens. So the objective lens cuts off all of the high frequencies in the diffraction pattern. Only the low spatial frequencies, low enough to make it through the lens. In fact, below a cutoff spatial frequency of NA over lambda, only those spatial frequencies are used to form the image. We often say that the objective lens acts as a low-pass filter, filtering out the high spatial frequency information from the mask. To help us mathematically, we're going to define a really simple function called the pupil function. Now, it may look like it's a little bit complicated. It is not. It is about the simplest function you can imagine. If I said, write an equation for a hole, what would you do? Well, this is it. A pupil function, now we have our spatial frequencies fx and fy, but remember those are simply scaled coordinates in the diffraction plane, in the plane of the lens. The pupil function is 1 whenever the spatial frequency is within the cutoff frequency, NA over lambda. That is, all the light that lands inside the aperture is transmitted. So this pupil function will be the transmittance of the lens. So 100% of the light's transmitted whenever the light is inside the aperture, and 0% of the light is transmitted whenever the light lands outside of the aperture. Now that is a pretty simple function. So it's a 1 or a 0. It's 1 when I'm inside the aperture and 0 when I'm out. right? Very fancy equation for a hole. But I'm going to use that right now because I have a mask that gave me a diffraction pattern. Remember, T sub m was the Fourier transform of the mask pattern. That's simply the diffraction pattern. I've got a pupil function, P, which I've just defined. Now, how would I write an equation for the light that goes through the lens? Well, it's simply P times Tm. I take the mask diffraction pattern, the Fourier transform of the mask transmittance, multiply by P, and that is the portion of the diffraction pattern that goes through the lens. Now, the lens takes the inverse Fourier transform of this light to produce the electric field of the image. I'll call that electric field E. So, the electric field of the image, as a function of x and y on the wafer plane, is the inverse Fourier transform of P times T sub m. That's pretty much all there is to it, except for one little thing. We're more interested in the intensity than the electric field. Our photoresist will react chemically to the intensity of light, and the intensity of light is the magnitude of the electric field squared. Another way of writing that is the electric field multiplied by its complex conjugate. Often our examples, the electric field will be purely real numbers, and so we simply take the magnitude squared. Okay, that's how we calculate an image. That's how we know what the image will be. Let's go back to our simple example. We'll come back to our simple example of lines and spaces in the very next lecture, lecture 43. Now let's take a look at what we've learned so far. You should be able to easily answer these questions. If not, you may need to go back and review the material. First, define numerical aperture. Next, what are the entrance and exit pupils of an imaging lens? How can one determine which diffraction orders will make it through a lens? What is the pupil function of a lens? What does that term mean? And explain the concept of Fourier optics. Well, that's our lecture 43, an introduction to imaging. What we'll do next time is work an example and calculate an image for the case of equal lines and spaces. Till then.